This video is going to provide a very short overview of organic chemistry. You need to realize here we are barely touching the surface of organic chemistry. This would be, a 2-semester class in college, but we want to make sure we at least touch on this stuff for AP because even though it's not tested explicitly on the AP exam, what happens is some of the questions use organic molecules or relate to organic a little bit. So sometimes having this knowledge can actually make the question a little bit easier, or seeing the molecules doesn't scare you as much because you're a little bit more familiar with it. So again, even though this is not explicitly tested on the exam, understanding this stuff can actually help you answer questions. So we're going to do a little bit of organic chemistry in this video, but again, we are barely touching the surface here. Remember, organic chemistry here is the study of carbon-containing compounds. So we're just looking at one element and kind of giving it its own kind of branch of chemistry. So organic chemistry is just looking at carbon. Remember, carbon's kind of unique here. It has 4 electrons in its outer shell, so 4 valence electrons, and it has room for 4 bonds here. It can form 4 bonds, possibly with 4 other atoms. Right? Or maybe it can do like double bonds with just, 2 atoms here, or maybe having even a triple bond involved. So it's kind of unique. You need to realize that many foods, gasoline products, vitamins, so on and so forth, are made from these carbon-containing compounds. So organic chemistry kind of applies to a lot of areas here. Right? Anytime we're looking at these carbon compounds, we're going to be doing organic chemistry. When carbon is bonded to 4 atoms or groups here, it has this tetrahedral molecular geometry with a 109.5 bond angle. If you remember, the bond angle for tetrahedral is 109.5. Because these bonds are 109.5, we draw a chain of carbon atoms in a zigzag pattern. Right? We don't show it as a straight line in organic chemistry. So you can see here how this would look, all right, all together. And typically, this is a very common way we would actually show these organic molecules. You can see it just looks like a bunch of lines there that are kind of zigzag together. If you ever see this format, you need to understand that at every point, there is a carbon atom. So there would be a carbon atom here on each end. Then at every point where it kind of then bends in a different direction, there's also a carbon atom. So this particular molecule that's drawn here would have 5 carbon atoms in it, one on each end and then at each of the points. But then realize the number of hydrogens that would have to be attached to each. They don't show the hydrogens in these kind of organic drawings like this. So you just need to figure out, okay, how many hydrogens need to be there to make that carbon happy. So the end carbons would need 3 hydrogens on each, because each carbon, if you imagine here, this carbon is attached to this carbon, so that's 1 bond, so it would need 3 more bonds. Okay, so the carbons on each end are going to have 3 hydrogens attached, but then each of the carbons here in the middle would be attached to just 2 hydrogens, because each of these carbons is attached to 2 other carbons. So that would give a total of 4 bonds here. So you need to understand what's actually happening here when you see kind of an organic written like that. You need to understand that kind of at the ends and each of the points you have a carbon atom, and then you need the hydrogens there to kind of make the number of bonds work for each of the carbons. This is the way we typically see organic molecules drawn in this zigzag pattern, and not even showing the carbons or hydrogens necessarily in the actual structures. If you hear the term hydrocarbons here, you need to realize that this is just going to be a compound that has just carbon and hydrogen in it. Obviously, it's organic because it has carbon, but it's just going to consist of carbon and hydrogen. Obviously here, carbon-to-carbon bonds can either be single bonds, you could have carbon-carbon double bonds, or carbon-carbon triple bonds in these molecules. But it would change the number of hydrogen attached here. Remember, you have to still satisfy the octet rule. Each carbon needs 4 bonds. These hydrocarbons can be really small molecules, something like methane, CH4, all the way up to really large chains of molecules here. So you see this particular example would have what, 1, 2, 3, 4, 5, 6 carbons in it. But then look at stearic acid, which is a long chain of carbon atoms here with then some other groups on the end of that. So these hydrocarbons can be really small, really long. It just kind of depends here, but understand that they're going to have just carbons and hydrogens in them, and each carbon still needs to be happy according to the octet rule. Some general characteristics here of these hydrocarbons: their bonds are going to be nonpolar. These large hydrocarbons are always going to be nonpolar. So that's actually very helpful. If you see these in examples to questions on the AP exam, if you just have, CH compounds, they're going to be nonpolar. And then depending on the question, that kind of keys you in a little bit here. Might even save you some time, just realizing that the hydrocarbon is going to be completely nonpolar. As you increase the number of carbons here in your hydrocarbon, some things happen. So the density will go up. That kind of makes sense. As you increase the number of carbons, you're going to get more dense. The viscosity is going to increase, so the resistance to flow is going to be greater. Your boiling point will increase, and that makes sense as well. If you think about this in terms of the IMFs, if you have more carbons, you're going to have a greater molar mass here. If all you have taking place are these LDFs, because these are completely non-polar, more carbons mean greater molar mass, means more electrons. More electrons mean you're going to have a greater polarizability. So that means your IMFs are going to be more, they're going to be stronger. So it makes sense that the boiling point is also greater as well. So this is actually a good review of that idea of more electrons mean more polarizable, which means greater or stronger IMFs here. As we increase those number of carbons, that's what we would expect happening. But there's kind of one here that's kind of opposite. You would actually see a decrease in the volatility or the vapor pressure. If your IMFs are greater or stronger here, as you add carbons, as you increase the number of carbons, that volatility is going to decrease. The IMFs are stronger, so it's keeping it together a little bit more. Less can enter the gas phase as easily, which would lower the volatility, lower the vapor pressure. The examples here on the bottom are kind of showing this idea in terms of boiling point. You can see we go from methane to butane to hexane to octane. We are increasing the number of carbons as we go to the right here. And you can see if you look at the boiling point, as we add carbons, that boiling point does go up. And it ties in directly with the IMFs and the polarizability here. So these are some characteristics of hydrocarbons that you definitely need to know. It can actually be very helpful in problems. These hydrocarbons, these carbon-carbon chains can actually be straight chains, kind of something like this, where you just have kind of this zigzag pattern of carbon atoms. They can be branched, which would mean kind of you have your zigzag pattern here for the main carbons, but then you kind of have another carbon group sticking off of one of the carbons. That would be branched. They can even be in a closed ring. All right, so as you can see over here, the carbons actually attached to each other in this closed ring, and the hydrogens are still attached to that. So there's kind of a few ways here that these carbons can actually join together. We should already be familiar with naming some of these basic organic compounds. We've already done this: the alkanes, the alkenes, and the alkynes. So this is just going to be a quick review of this. Remember, we're naming them with prefixes based on the number of carbon atoms present. So the prefixes are close to the prefixes you would use for covalent naming, but realize the first four here are kind of different from covalent naming. All right. The meth, eth, prop, bute are different. All right. If you had one carbon, that would be the prefix meth. 2 would be eth. 3 would be prop. 4 would be bute. But then you can see it kind of follows normal covalent prefixes: pent, hex, hept, oct, so on. All right. So definitely be aware of these prefixes and realize the number of carbon atoms here in these hydrocarbons are going to tell you which prefix to use. Nothing really new here, just realize that alkanes have the general formula there with your carbons and your hydrogens, but your hydrogens are 2 times the number of carbons plus 2, all right? These alkanes are going to have all single bonds. So realize here, if you were to get an alkane in a problem on the AP exam, knowing that, oh, here's a substance that is an alkane, knowing that it has all single bonds, you can quickly draw it if you need to, or know how these things are bonded together here. Right? So this is why some of these little things are very important. If you have an alkane, you know how it's named, you can actually, quickly realize, hey, look, it's going to have all single bonds when you have to draw it or do the structure. We say that it's completely saturated here, meaning it has the maximum number of hydrogens that it could possibly have. And because of this, the alkanes are going to be the least reactive of the 3 groups. We know that to name it, you use the correct prefix, and then you add the ane ending. You would know a formula is going to be an alkane based on the fact that you can see the hydrogens are times 2 plus 2. To do the formula, the prefix tells you how many carbons to put, and then you do the math here to figure out the number of hydrogens. So you can see the 2 examples. Obviously, you need to be able to do this. You need to be able to take a formula and get it into the name. Again, use the number of carbons for the correct prefix, and then you can see here that to get the hydrogens, we have to do times 2 plus 2, so that makes it an ane. Obviously, you need to be able to get the formulas as well. So this is not really anything new, but pay attention to these things here. The alkanes are going to have times 2 plus 2 for the hydrogen, all single bonds completely saturated, making them the least reactive of the 3 groups. Alkenes then have the number of hydrogens just being times 2 the number of carbons, so no plus 2 here. These actually have 1 double bond in them. So if you could, you're given an alkene on the AP exam, you would quickly know, oh, there's going to be a double bond in there somewhere just by having this, a little bit of background information. These are unsaturated because they don't contain the maximum number of hydrogens that they possibly could because of the double bond. You need to use the correct prefix, though, with the "ene" ending. And if you're doing the formula, the prefix tells you how many carbons. And then once you realize it's "ene", you know you need to do just times 2 to figure out the hydrogens here. So again, you can look at those 2 examples. Make sure you're good with this. This is a review, though, but you need to know those alkenes are just times 2 for the hydrogens here. And then finally, alkynes, they're going to be for the hydrogens times 2 minus 2, okay? So you take your number of carbon atoms times 2, subtract 2 to get the number of hydrogens. Alkynes are going to have a triple bond in them. They are also going to be unsaturated because they don't have the maximum number of hydrogens that you could have here because of that triple bond. But they are going to be the most reactive of the 3 groups here because of that triple bond that can easily kind of be attacked, if you will, and can undergo some reactions. So these guys are going to end with YNE. As soon as you see a formula here, a name that has YNE, you know that it's going to have a triple bond in it. It's going to be an alkyne. Obviously, to do the formula, the prefix tells you how many carbons, and then based on the YNE ending, you do the math, times 2 minus 2 to get the number of hydrogens. 2 more examples here for you to see. Make sure you're good with this. Definitely understand that the alkynes are the most reactive. They have that triple bond, and the hydrogens are times 2 minus 2. Cycloalkanes are just when you have these alkanes, basically, but they're arranged in a ring or a cyclic structure here. And sometimes we actually use symbols to represent these, as you'll see. But this is the basic idea of some of these cycloalkanes. You'll never need to name them for me. Again, we're just doing basic overview here of these. So for the cycloalkanes, you won't need to name. But you can see if I have 3 carbons kind of in a ring, that would be cyclopropane. All right, for the 3 carbons, cyclobutane, cyclopentane, and cyclohexane here. But again, sometimes we actually use symbols here, and we don't show any of these C's or H's at all, as you'll see. Here's just a picture showing you how we can use symbols here to represent these cycloalkanes. So a triangle would represent cyclopropane, a square would represent cyclobutane, and so on. If you actually needed to name these and you have other groups attached to these ring structures, we call those things substituents. Substituents are just these groups that are attached. If you were to have these groups attached and you need to name this, you would have to number the carbon atoms in a way so that your groups would have the lowest number possible. So for example, if you had one group sticking off of one of your carbon atoms here in cyclobutane, you would number in a way so that that group would be on carbon 1. You wouldn't want that group on the fourth carbon, if you will. All right. So anytime you hear the word substituent, just realize that means we're attaching groups here to these things. And again, you're not going to need to name these for me, but if you do see any naming with these, understand that when you get to organic chemistry, you will see numbers. These names get very complicated. Like I said, we just doing kind of the easy ones with the alkanes, alkenes, and alkynes. But if you did need to name these and you do see numbers, the numbers of your groups need to be in a way so that you have the smallest numbers possible here. Benzene is a special kind of ring structure here. It's an aromatic compound based on this benzene ring. So you have these 6 carbons in a ring here, but they have these alternating double bonds. So you have a double bond between these 2 carbons, then you skip, double bond between these 2 carbons, then you skip, and then a double bond between those 2 carbons. It actually has resonance here because of that, and it can shift. They actually draw it with this circle in the middle. So it's your hexagon here with the circle in the middle, and that indicates, or that's kind of the structure they use to represent benzene, or C6H6. Again, this is just more for your information. You will definitely use this a lot in organic chemistry. This brings us to isomers here. All right, the first isomer we're going to look at is called a structural isomer. So you need to know the definition here first. Structural isomers are compounds that have the same molecular formula, but they're going to be connected differently. So it's going to be, you're going to look at 2 different compounds here that have the exact same formula, but how they're arranged, how they're connected together here are a little bit different. Because the structures are different, even though they have the exact same formula, this leads to different properties. So let's look at an example here. C4H10. Well, that's butane. So normal straight chain butane here is just 4 carbons in a row with the correct number of hydrogens attached. Well, that's used as a fuel source. We use it in lighters. But then a slightly different form of butane, isobutane, has the exact same formula, C4H10. But notice we have 3 carbons kind of would be in a line here, and then the other carbon is attached to the center carbon. It kind of is branched here. Well, it's the exact same formula, but a different structure. All right, this actually has totally different properties. It's used as a refrigerant. So even though they have the exact same formulas, because they are connected differently, they have different properties. These are called structural isomers. So if you need to be able to identify structural isomers, you have to see that first they have the exact same formula, and the only difference is how they are connected together. Essentially, their structures are different. So you need to be able to pick these out if you're given kind of 2 examples to compare. You need to realize here that you could actually have a lot of structural isomers for a particular compound. You can see in this picture, here are 5 structural isomers of hexane. They all have the formula C6H14. The only difference is the way in which they are connected. So here's normal straight chain hexane. All right. Here you can see a version where you have kind of this carbon group hanging off of the second carbon in the main chain. So you have a main chain of 5 carbons here, and then another carbon kind of sticking off the second carbon. Here we have that same 5 carbon atom chain, but this time the carbon atom is going to be sticking off of the middle carbon. Down here, we have a 4-carbon chain, and then we have kind of 2 carbon groups sticking off of the middle carbon atoms. And here we have another 4-carbon chain, but then 2 carbons are kind of hanging off of the second carbon in that chain. So if you notice, they all have the exact same formula. They all have C6H14 if you actually looked at this, but the only difference here is the way in which they are connected to each other. So these would all be structural isomers of each other. The next type of isomer here is called geometric isomers. Again, these are going to be compounds that have the same formula, but they are going to be different in their 3D spatial arrangement here. Okay, so you need to understand that a lot of times this geometric isomer is going to exist around a double bond. Just having a double bond in a molecule doesn't mean it's going to be a geometric isomer. That idea is important, but realize if you have a double bond here, you might have this geometric isomer kind of taking place here. So let's look at the difference here. So you can see in this molecule on the left, we have these 2 carbon atoms double bonded. Then you see we have CH3 groups kind of on top. You can kind of see there's 2 different sides here to this double bond. There's kind of a top side and a bottom side. So the top is where both of these CH3 groups are, but the bottom, you just have hydrogens. We would call this the cis version, basically because the groups here, or the things attached, in this case the CH3s, the groups that are not hydrogen, the CH3s are both on the same side. Cis meaning same, all right? So the CH3 groups are both on top, if you will, so we call this the cis version of the isomer. But then notice on the right here, the CH3 groups are kind of opposite. You have one CH3 group on top and the other CH3 group on the bottom, and then your hydrogens are kind of alternating as well. Because they are on opposite sides here of that double bond, one's on top, one's on the bottom essentially, we would call this the trans version, right? But notice all that they are different by are their 3D spatial arrangement here around that double bond. Okay, so when we're looking at these geometric isomers, typically we see a double bond, but just having a double bond doesn't make it geometric. You need to actually see these groups being, on the same side and then being on the opposite side. All right, that's what makes these different. This one has the groups on the same side. This one has those groups that aren't hydrogen on the opposite side, which leads to these geometric isomers. You need to understand here that this is usually going to occur around these double bonds because this double bond is very rigid. It doesn't allow for this rotation to take place. If this was a single bond, these atoms could just rotate all they wanted, and you really wouldn't have these opposite sides here. Because the double bonds are so rigid and there's this restricted rotation, all right, these atoms can't really rotate around the axis of the bond. This leads to this cis-trans idea where you get same side versus opposite side. You kind of get this top and this bottom here because of this rigid or restricted rotation that's caused by the double bond. So make sure you understand this idea of why this is taking place. But geometric isomers are going to have the same formula. They're just going to have a different 3D spatial arrangement of these atoms, typically around a double bond. The last type of isomer we are going to look at is called here enantiomers. These are a little tougher to identify, but again, they're going to have the same formula, but these molecules are going to be mirror images of each other. So essentially, they cannot be superimposed on one another. Obviously, it's going to be just like the idea of your left and your right hand. You can't put your left and your right hand on top of each other and make them match up. All right, they're mirror images of each other. You can put them together and they match up, but you can't set one on top of each other to make them match up. And that's the same idea here with these enantiomers. If you had your enantiomer and you put a mirror between or by it, you would see the other version of it in the mirror essentially. All right, they cannot go on top of each other. They can't be superimposed on one another. They still have the same formula, but they're just going to be mirror images of each other. A really good example of these enantiomers in the real world here, having these different kind of structures leading to different properties. Way back here in the late 50s, 60s, there was this drug called thalidomide. It actually had two different forms of it, but they didn't know it. So what happens here is the R form, which you can see here on the left, actually helps pregnant women with nausea. All right. But the S form is a teratogen. Basically, it causes birth defects. Well, when this was given to women to help their nausea while they were pregnant, they were giving it to them in a mixture of the two. So they were helping their nausea, but actually causing birth defects in the process. All right. Because they are mirror images of each other, they have different properties. Even though they're the exact same formula, they're slightly different because they are mirror images. They can't be superimposed on one another. They're enantiomers. Because they have these slightly different kind of setup, it led to different properties, and then unfortunately kind of led to some issues here because they were being given both. Enantiomers are a little harder to pick out, but you need to realize they have the same formula. They're just going to be mirror images here of each other. You can see the three different types of isomers here that we looked at. Again, they are all going to have the same formula, but structural isomers are going to be different in the way they are attached. So maybe see like some branching taking place. Geometric isomers are when you have this kind of difference in your 3D spatial arrangement. So cis would be when they're on the same side. Trans would be when they're on opposite sides, and this usually occurs around a double bond because the double bond has this restricted rotation, or it's very rigid, doesn't allow for this rotation. And then enantiomers are the last type, but they're just mirror images of each other. So obviously you should be aware of the three types, and if you're given examples, be able to identify which type of isomer you are looking at. This brings us now to functional groups. All right, functional groups are just these atoms or group of atoms that you can add to your hydrocarbon. So these are just groups that you could add to your alkane or your alkene and so on. All right, these are functional groups that we will see in organic chemistry here. There's actually a lot. We are going to focus on these 7. So you are responsible for identifying these and knowing kind of what's going on with each, and maybe even being a little bit familiar with how they're named. So when you look at these, anytime you see an R here, that just means you have some hydrocarbon, some organic molecule here. Could be a long chain of carbons and hydrogens, could be just one carbon with hydrogens, but the R just indicates there's some organic group here. So if you see a molecule, you have this chain of organic molecules, and all that you have sticking off the end of it is an OH group, that's an alcohol. All right, alcohols kind of have these OH kind of sticking off the end, but then the R part is just some organic here. It could be a lot of carbons and hydrogens. It really doesn't matter. To name them, they would end in OL. Just like alcohol, it would end in OL. So if you saw something like ethanol, F tells you there's going to be 2 carbons here, and then the O tells you you're going to have the OH sticking off the end. So you need to recognize these by the organic with the OH sticking off of the end. Ethers are when you have this O kind of in between 2 organics here. So you have some kind of organic attached to oxygen, and then you have that oxygen attached to another organic. So it's kind of like the oxygen is smushed in between these organic molecules, but it's all single bonds. So we say this is an ROR version. To name these ethers, they would be like an oxyane. So you can see here, if you saw something like methoxyethane, that's telling you that this is an ether. Again, you don't need to go too crazy into this, just recognizing like, oh, this would be an oxyane. Seeing here, understanding that you kind of have this ROR, this oxygen kind of single bond in the middle of 2 organics, you would be able to identify that as an ether. An aldehyde is when you have some organic and then you have a carbon with a double bond to an oxygen, and then that carbon is attached to a hydrogen. And that's kind of ending your molecule here. So you have some form of organic group, and then your N carbon has a double bond to oxygen, and then that carbon is attached to a hydrogen. We call that an aldehyde, it would end in al. All right, so C double bond O with an H sticking off of it, that's an aldehyde. A ketone is very similar to that. You're going to have this C double bond O, but instead of the H sticking off it, you have another organic group, so another carbon hydrogen. All right, so you can see the difference here. You have some organic, and then your carbon here has just a double bond to an O. So if you see kind of some crazy organic molecule with just a double bond to an O in it, it's going to be a ketone. They would end in -one. So something like propanone tells you there's a C double bond O there somewhere in your molecule, but it's got to have some type of carbon organic group kind of hanging off it, different from an aldehyde, which just has the H kind of hanging off of it right there at the end of one of these molecules. For a carboxylic acid, you'd see some organic, and then your last carbon would have a double bond to an O, and then that carbon would be attached to an OH. It's kind of like you're combining an alcohol with a ketone here. So you see C double bond O, and that carbon is attached to an OH. We call this a carboxylic acid. It would end in oic acid. Sometimes you just see these written as COOH compounds. So again here, this is just helping you understand how this would be set up. Let's just say you got an example on an AP exam and you were given the name of a compound and you saw oic acid. In your head, you would be saying, okay, I know it's going to be set up in some way that I have a C double bond O and that carbon is attached to an OH. It makes the problem much easier here for you to understand how it's going to be bonded together, how it's going to be grouped, maybe even the properties of it. All right, because you would kind of know a little bit about how it's bonded together here. An ester is when you have some type of organic, you have your carbon double bond to your oxygen, but then that carbon with the double bond to the oxygen is attached to an O, and then there's kind of another organic group hanging off of that. So you see this C double bond O, and that carbon is attached to another O, which is attached to another carbon group. That's called an ester. So these typically have a like IL and O8 naming scheme. Again, the naming is not super important here, but understanding what this would look like, being able to identify a molecule as an ester because of that C double bond O, and then that carbon with the double bond O has an O with another carbon group attached to it. And the last one you're responsible for knowing are amides. This would be when you have that carbon group attached to a C double bond O, and then you have like an NH2 group sticking off there, an N, some type of N group hanging off of that. That would be an amide, and we name them using just kind of the word amide here. So C double bond O with this N group hanging off of your carbon, that's going to be an amide. So definitely be able to recognize these 7 groups. If you're given a molecule, you could identify the molecule as being one of these or 7 types or having one of these 7 functional groups in them, and be a little bit here aware of the naming scheme just so that it could possibly help you in problems. On this particular slide, I just want you to see that there are definitely many more functional groups in organic chemistry here. You are only required to know the 7 that I just showed you on the previous slide, but realize there are actually a lot, and they each kind of have their own naming scheme here, and you can see and look at them and see what some of those different functional groups might look like, but you're only responsible for the 7 on the previous slide, being able to identify them and have a basic idea of how they are named.